density of unit cell. Density of unit cell here, that is density is equal to Z into M upon A cube into Avogadro number. Now here rho, that is density of unit cell, Z number of atom per unit cell, A edge length, M mass of unit cell or mass of unit cell or atomic mass or molecular mass, where Na is Avogadro number, that is 6.023 into 10 to the power 23 per mole. This is the density to calculate. Here one unknown value is given and another by putting to find the unknown value, right? Now, after that here we will calculate the next part, that is defect, or it is known as imperfection. Defect or imperfection. This defect or imperfection, that is are two type. One is point defect and other one is line defect. Point defect are classified into two types. One is stoichiometric defect, non-stoichiometric defect. This stoichiometric defect again classified into following. One is Schottky defect, second one is Frankel defect, then impurity defect, and non-stoichiometric are classified into two types. One is metal deficiency defect and metal excess defect. Here this is the classification of. Here also you can write vacancy defect. These are the classification of defect. Defect means imperfection, that is not perfect. Not perfect means some error is there. So here point defect, in which in a crystal or in a unit cell, a small point where there is a error, and in case of line defect it is a complete row. Defect is in complete row, that is, and also it is studied in your higher class, that is in your higher class. So here only we will discuss with the point defect. This point defect again classified into stoichiometric defect and non-stoichiometric defect. Stoichiometric defect again classified into Schottky defect, Frankel defect, impurity defect, vacancy defect, and non-stoichiometric defect are metal deficiency defect and metal excess defect. Now here we will discuss, that is defect. See, this is a unit cell. This is a pure crystal. From this crystal, when defect arises, there is a formation of see here one cation and one anion, that is cation anion is missing from the side. अपने क्रिस्टल साइड से एक केटायन और एक एनायन मिसिंग होता है, दैट इज सेड टू बी शॉर्टकी डिफेक्ट. Schottky defect. So here one cation, one anion is missing. So here one cation, one anion is missing from the crystal side, and that is one cation, one anion is missing. That is example AgBr. See here we can say only one cation and one anion is missing to show defect, and that is stoichiometric defect. Similarly, Frankel defect, here in this Frankel defect only cation is missing from side and present in a void, है ना. यहाँ पे क्या होगा, ये प्योर क्रिस्टल, this is pure crystal, from this pure crystal one cation is missing, एक cation यहाँ से missing and present in a void, बाकी सब अपनी जगह पे ही होंगे, that is said to be Frankel defect. Cation is missing and present in a void or interstitial site. Here also example AgBr. And the question is that when in case of Schottky defect, mass of unit cell, density of unit cell, and volume of unit cell. Here mass, density, volume. Mass, density both decreases. Volume of unit cell remains same. Now, in case of Frankel defect, mass, volume, density all are same, that is constant, because one positive charge is removed from its side and present in a void, so no change in mass, volume and density. Now, impurity defect, a defect in which pure crystal is treated with strontium or cadmium. One strontium ion is replaced two sodium ion, because strontium is bivalent and sodium is monovalent, so that there is one vacant space. See, this is a pure crystal. This is a pure crystal of NaCl or KCl. Now, when this crystal is treated with bivalent like cadmium or strontium, so what happened? One of the strontium is added, and now negative, here also negative. There is a vacant space. This is a vacant space, and this vacant space arises due to the addition of this bivalent ion, because we know that one bivalent ion is equal to 2 sodium ion, and that is said to be impurity defect, or it is also known as vacancy defect. Next, that is non-stoichiometric defect. This non-stoichiometric defect is that where defects are not balanced, not neutralized. Now see here, there is a one, that is metal deficiency defect. According to the name, metal deficiency, in which metal is less as compared to non-metal. So here these defects are shown by the metal which undergoes variable oxidation state. Such type of defect are responsible for those metal ion which show variable oxidation state. Now let's example, iron show Fe2 plus Fe3 plus, nickel show Ni2 plus Ni3 plus. That is the variable oxidation state. More than one state it is stable. Now after this, here it is proved with example. See, suppose that given Fe 0.96 O 1.00, so here Fe is also written with 96 O 100, multiplying by 100 both, so you will get this. Now here I am writing Fe is equal to Fe2 plus Fe3 plus, because iron contain both the valencies plus 2 plus 3, but oxygen is always O2 minus. So here when it form a compound, this iron and this is oxide, iron, that is Fe2 plus plus 3 plus equal to O2 minus. Let Fe2 plus be X, Fe3 plus become 96 minus X, and O minus 2 is given 100 complete. So here by putting in this equation, Fe2 plus Fe3 plus is equal to O2 minus Fe2 be X plus 96 minus X is equal to 2 into 100. Here so 3 into its valency, 2 into its, so it is 2x plus 3, 288 minus 3x is equal to 200. Therefore x is equal to 88. Now therefore Fe2 be 88 and Fe3 is equal to 8. Now therefore Fe2 plus percentage is equal to 88 upon 96 into 100, and Fe3 plus percent is equal to 8 upon 96 into 100. So here on solving, you have Fe2 plus B 91.6. The total percentage of Fe2 and Fe3 is 100, but not separately 100, so that it is deficient from the oxygen. So it is said to be metal deficiency defect. One more example, that is for you all, given as here, say Ni 0.98 and O 1.00. You all solve in this way. Ni is equal to Ni2 plus and Ni3 plus, same as O is equal to O2 minus. Now on equating value, to get percentage of Ni2 plus and percentage of Ni3